Right, so we're going to finish up this week looking at section 6.4, which is on the graphs of all the other trig functions we haven't studied yet. All right, so for our first one, what we're going to do is kind of use what we know about tangent to rewrite it and figure out what it would look like. All right, we already know a lot about sine and cosine. So using that knowledge, we can figure out what tangent should look like. How can we rewrite tangent in terms of sines and cosines? Sine over cosine. Right. Now, I want to focus on when tangent would equal 0. What's the only way tangent would equal 0? And it's focus on the right-hand side and figure out when that would be 0. Yep.
Well, when sine x is 0.
Yeah, whenever you make the numerator 0. So somehow we have to make sine of x 0. Right? And there's a couple places where that occurs if you think of the graph of sine. Right? So we'll come back to that. And when would we get vertical asymptotes? When what? Yeah, anytime the denominator is 0, because there's no common factor in the top, so we're not going to get a whole. Whenever the denominator is 0, we get a vertical asymptote. Right? So now we've got to visualize the graph of cosine in our head and see where that's 0. And then once we have our asymptotes, we can just test a value on each side. Usually what happens is when you get very close to the asymptote, you go up to infinity and down to negative infinity on the other side. Right? So this is where we're going to check values like if the asymptote was 3. We would check 2.99 and 3.01. We'll do that kind of stuff. All right, so when is sine 0? Anybody give me one value I would plug in for x, take the sine of it, and the answer would come out to 0.
0.
Yep, 0. What's another value you could plug in for x? Take the sine of it, and y comes out to 0.
1.
Think in terms of pi. So x's are all going to be angles in terms of pi.
Sine of pi.
Yep. If you take the sine of pi.
2y.
Let's see, 0 pi, yep, 2 pi. Okay. Basically, it's 0 plus or minus any multiple of pi. Those are all the times you can take the sine and get zeros. All right. What's our first positive angle we can take the cosine of? And it comes out to 0.
Zero.
Not 0. If we take the cosine of 0, we're going to get 1. Pi over 2. Yep. So pi over 2. Take the cosine of that, we get 0. What's the next time cosine crosses the x-axis? 3 pi over 2. And what's the difference between pi over 2 and 3 pi over 2? How much? Yeah, it's a difference of 2 pi over 2, or pi. All right? So basically, yeah, we can add or subtract from pi over 2, add or subtract pi as many times as you want, and you'll get more and more asymptotes. Okay, generally when we sketch it, we're going to focus on one period of tangent. Okay, so let's see if we can graph that. All right. So first thing I'm going to do is put in my zeros. So when x is 0, I'm going to cross the x-axis. At pi I'm going to cross. 2 pi I'm going to cross. And we could keep going, but this will give us enough sections we can sketch it. And I'm going to have asymptotes at pi over 2. I'm going to have an asymptote at 3 pi over 2, 5 pi over 2, and so on. Once we figure out what tangent looks like in one of these sections, we can just copy it to as many sections as we want. All right, so let's type in tangent. You can turn your calculator on. All right, so tangent Okay, I'm going to do it in radians. And what would be a value? Well, let's look at what pi over 2 is, in case you're not sure what number that is. I'm sorry. Pi over 2.
Type in 2 pi.
Oh, I was going to say, yeah, that should be undefined. Pi over 2. 2. Enter. Okay. So 1.57. What's a value just after 1.57?
1.5.
Sure. 1.58. Okay. So when we type in 1.58, we're way down. Okay. Way down here. Okay. Now I'm going to type in a value just before 3 pi over 2. Yeah, it's going to be way up. Okay, if you're not sure, that's 4.71. So let's try 4.70. Okay, just before it. And as Aiden said, of course, we're way up, in this case, at 80. All right, so let's make that bigger. Not that big. All right, so now we're way up. All right, so basically we got to connect this dot at the bottom to the one at the top. We got to go right through pi, and it has to be a curve. Okay, so it's going to look something like that. And if we copy and paste that to other sections, we get the graph of tangent. Okay, so it looks like these repeated curves. I'll just do zoom 7 so you can see it. If I was asking you to show me a certain number of periods on the test, I wouldn't like this window because it's cutting off periods halfway. Okay, so we'll try to find nice windows. But we're looking a little over 5 periods here. Okay, a little over 5. But not quite 6. This is not quite half, and that's not quite half. But there's your graph of tangent. Okay, any questions on that? All right, now for cotangent, we could really go through all the same things, except the only difference is sine and cosine do what? They switch. So that means between tangent and cotangent, all your zeros for tangent become your what in cotangent? They become your asymptotes, and all your asymptotes in tangent become your zeros in tangent. Yeah. Well, it actually doesn't shift it. It also ends up, the curve goes the other way. Okay, the curve ends up going the other way. Okay, so it ends up looking like that. We could easily prove that just by typing it in. Check 0.001, check 3.13, and you would see that. And if you want to type it in on the calculator, there is no button for cotangent. So it's 1 divided by tangent. And there's our graph of cotangent. Okay, any questions on that one? All right, so we got our graph of tangent, and this is cotangent. Okay, notice how often that tangent and cotangent repeat. Okay, with sine and cosine, how often did they repeat if you didn't alter them?
Every 2 pi.
Every 2 pi. But notice what would happen if you went to 2 pi on cotangent. How many times would it have repeated between 0 and 2 pi? It would have repeated twice. Okay? So for cotangent and tangent, you only need to go pi radians, or 180 degrees, to see a full section. Okay? Same thing here. Okay? Pi over 2 to 3 pi over 2, that's the difference of pi radians. All right, so the natural period for tangent and cotangent is a little shorter than sine and cosine. It's just pi. Okay, and another way we can say that as an equation is that tangent of any value is equal to tangent of that same value plus or minus any multiple of pi. Right, so as an example, if I took, right, somebody give me an angle in radians. Besides pi, because I'm going to add multiples of pi, that'll be confusing.
3 pi over 2.
Sure, 3 pi over 2. All right, so 3 pi over 2. Okay, that's an error, so let's, tell you what, I'll pick an angle. Let's just do the number 5. Okay, tangent of 5, negative 3.38. Now I can take that, and I can add pi, and I get exactly the same thing. Right? So basically, what I just did was, imagine putting a horizontal line in here, and pretend like this is 5. I know it's not quite 5, but pretend that that's 5. That same answer is going to repeat itself pi units later. And the next answer is going to repeat itself another pi units. Okay? Or if I wanted to find the answer before it, I could subtract pi. Right? But as long as you add or subtract multiples of pi, you're always going to get the same y value. Okay? It just keeps repeating all the way down the graph. Right? So we'll take tangent 5 plus 17 pi. Okay? What do you think I'll get? Same answer. I've just gone down 17 periods, but I'm at the same y value. Okay? Could I add non-integer multiples of pi? Like 1.6 pi? No. You have to add a full multiple of the period. Okay? You can't add half a period and get to the same spot. Okay? How about tangent of 5 minus 89 pi? Same thing. You've just gone back 89 periods on the graph. Okay? And that works for both tangent and cotangent. Okay. As long as you use integer multiples. 2 pi, 3 pi, 17 pi. N can't be like 6.2 pi. Okay, it's got to be an integer multiple. Okay, that's what that says. Okay, any questions on that idea? Okay, we did the same thing with sine and cosine. I think we called it the periodic property. I think that was the name of it. All right, so we've learned about all the transformations and how they affect sine and cosine. They're exactly the same for tangent and cotangent. Right, so if you have tangent, A would be your phase shift, B is your period change, C is your amplitude change, and D is your vertical shift. No difference. In fact, when we do secant and cosecant, it's also the same.
Don't they go up to infinity in negative phase, so how do you vertical stretch
You can still do a vertical stretch. In fact, I'll do
Stretch
one.
the middle part?
Yeah, it'll stretch out the middle part. Yep. We'll do a vertical stretch of tangent. In fact, I'll give you 2 graphs. I have one coming up. And I'll ask you to identify which one is tangent 2x and which one is tangent 5x. But if you think of it just like you did, that you're stretching the middle part, it would kind of straighten it out a little bit. The more you stretch it. All right, so any questions on this idea? It's exactly the same. Okay, remember A and B do the opposite, C and D, exactly what you would expect, all that kind of stuff. All right, so anytime I ask you to find the tangent, the period of tangent or cotangent, this is your formula. When we did sine and cosine, what was the numerator in the fraction? It was 2 pi. All right, so now you've got to be careful. Sine and cosine, everything revolves around 2 pi. Tangent and cotangent, pi. Right, and another thing I think it's helpful when you're trying to graph is to figure out where are your vertical asymptotes. Because if you can find those, then you've basically drawn yourself a section And that's what you're going to sketch in between those asymptotes. Okay, but you need to find them first. Well, the first positive asymptote for tangent occurs at pi over 2, okay, or 90 degrees. So if you just take your argument, okay, whatever they give you in the trig function, like tangent 2x, okay, take the argument, set it equal to 90, and that'll tell you where the vertical asymptote is. Okay, or it'll at least tell you where one of them is. And then if you know where one vertical asymptote is, you know that that asymptote reoccurs every period. Okay, it's going to keep repeating itself every period. And we can find more vertical asymptotes and sketch as many periods as we want. All right, so you're going to set your argument equal to 90, find one asymptote, and then add the period to that asymptote to get another one, or subtract the period, whichever way you want to sketch. I generally sketch, or try to sketch, somewhere near the origin. I don't usually sketch like the 23rd period down. I sketch pretty close to the origin. All right, so let's use that idea to see if we can figure out what this graph is going to look like. Y equals tangent 2x. Okay, even if I'm not sketching by hand, I probably still want to know where the first asymptote is, and I can use that to set my x-min and x-max values. All right. So somebody walk me through, how would I find where my first positive asymptote is here? Yep, Brian.
I'll start by saying tangent 2x equal to 90.
Do you want to set the whole function or just the argument?
Oh, yeah, just the argument.
Just so, yeah, what's my argument there?
So, 2x.
2x. Okay, so when that argument equals 90, if we're doing it in degrees, that's when we get a vertical asymptote. Right? So that would be when x equals 45 degrees, or in radians, pi over 4. All right, so now we know our first asymptote, and they want us to show 3 periods on the screen without cutting any off. So what is my formula to find the period of tangent? Autumn? Pi over, in this case you said 2, yes. So if we want to show 3 complete periods, what's the difference going to be between x-min and x-max? This would be for 1 period. 3 pi over 2. And you do x-max minus x-min. Whatever values you pick, it has to be a difference of 3 pi over 2. And that will show 3 periods. Mm-hmm.
Another way, like, could you also find like the asymptote? Could you just divide the period by like the p-value? Or does that only work in this case? It's like dividing pi over 2 by 2 is tangent of 2.
Could you divide? Yeah, I think most of the time you'd be okay. Let's see if that always works though, when we do other examples. Yeah, so he was just saying just take the period pi over 2 and divide by 2 to get the asymptote.
Well, not necessarily 2, but
whatever b is. Yeah. Yeah, I think that should usually work because you're basically taking, in this case we had 2x equal to 90, which would be like saying 2x equals pi. So when you divide each side by 2, you get x equals pi over 2. And then took your asymptote. Yeah, I think that would work, but I'd have to just double check it. Yeah. All right, so where should I set my x min at? So I get a nice graph here. Well, if we set it at 0, that's going to end up probably being in the middle of tangent,
Oh,
right? We're going to have an asymptote
you
at
just said the asymptote.
pi over 4, and you're going to have another asymptote at negative pi over 4, so 0 is right in the middle.
So you can negative pi over 4.
I would do pi over 4, or you could do negative pi over 4. Either, we could try both. Either one should work. So that's an asymptote. And now, how far to the right do I have to go from pi over 4 to show 3 periods? I want to show 3 periods. Yeah, so from pi over 4, I want to go 3 periods to the right. So that's 3 pi over 2. Okay, and that's how I always do it. I just let the calculator figure it out. As far as our y scale, remember tangent goes up and down forever. So we shouldn't need to adjust that. Let's hit graph and see if we get 3 nice periods on the screen.
Yep.
It's perfect. All right, now Aiden had said, could we do with a negative pi over 4?
I already tried it, and it gives you a little bit of a portion on
Right, just take that. Okay. On the test, you do not have to write these as decimals. This was pi over 4, and this was pi over 4 plus, I wanted 3 of the periods. All right, let's take a look. Let's try what Aiden said. So you said negative pi over 4?
Yeah.
And now I'm going to take that, and I'm going to add what? Yep, add 3 pi over 2. Okay, I'm adding triple the period because they said show 3 periods. And that should be perfect. The 2 on the right, those are 2 of the ones I was showing you before. Okay, we had, in my graph for that window, we had this one, and the next one. Okay, the way Aiden did it, he did the one before this one and this one. That's fine. Okay, any questions on that? Right, it does take a little practice to find the right window, but I think finding your asymptote and finding your period, that's the biggest thing. And then if they did want me to sketch by hand, well, once I have 2 asymptotes, okay, then all I have to do is check a point just to the left, just to the right, and find out which way it curves. Okay, but I would try to remember that tangents always curve like this, up and to the right. Cotangents are down and to right. Okay. All right, so if we look at this one, which one is the graph here of 2 tangent x, and which one is the graph of 5 tangent x? Jacob?
The one on the left, the 5 tangent x.
Yep, this is the 5 tangent x. And this is 2 tangent x. How'd you know that?
It's stretched out straighter.
Yeah, it almost looks like they're straight, because what's happening is the more you stretch it vertically, the more you lessen this curve. Okay? If you were to compress it, we could really make this curve even more pronounced if we compress it. Okay, any questions on that type of problem? All right, so just like we did with tangent and cotangent, we'll take a look at how we can figure out secant, what it would look like by hand. But we're not going to go through it twice for cosecant. Okay, so secant is what you get when you flip cosine. All right, where would you get a vertical asymptote for secant? Whenever what happens?
Cosine 0.
Yeah, whenever you make the cosine 0. Okay, let's just write down a few of those values. What could you plug in for x here? Take the cosine of it, and you get 0. Or think of when cosine crosses the x-axis.
Pi over 4? Is it pi over 2?
Yep, pi over 2. So that's at 90. When else does cosine cross? Brian?
3 pi over 2?
3 pi over 2. 5 pi over 2. And so on. Okay, keep adding or subtracting multiples of pi, and you'll get more and more x-intercepts. All right, so I think that's pretty good. All right, next thing I want to figure out, will secant ever equal 0? No, because it's always a 1 in the top. Okay? Secant, the only way secant could equal 0 is if somehow you could make the numerator 0, and you can't. Right, what would happen if cosine was equal to 1?
Then
What would secant be?
1.
1. Right, so if cosine is 1, secant is 1. All right, and now I'd be thinking in my head, all right, what values of x would I plug in that give me a cosine of 1? Well, 0. Cosine of 0 is 1. And we could keep going. 2 pi. Cosine of 2 pi, or 360, is also 1. What about when cosine of x equals -1? What would secant be? It would be -1. Does anybody see some values that secant can never hit? It'll never hit 0, yeah. So it's never going to cross the x-axis. It can hit anything above 1 or it cannot. Well, cosine is always a number between what? No, not 0. What's cosine always between? When we graph cosine, what's the range? 1 to -1. So you're always taking 1 and dividing it by numbers between -1 and 1.
So it can't be larger than -1. No, it can't be smaller than -1.
It can't be, yeah, it won't be. So when you say smaller, what do you mean, like on a number line? Like there's 0, 1, -1.
Well, it can't be between 1 and -1.
Yeah, you're never going to get a value between 1 and -1. Okay, that's not possible. For you to get values between 1 and -1, you'd be getting fractions. Well, to get fractions, you'd have to have cosine being a big number, like 2, 3, 4. Cosine is never any bigger than 1, okay? Which means this fraction can never be between -1 and 1. Okay? Secant is always either bigger than 1 or smaller than -1. Right? So if you think of a graph of the range, it would look something like this. Any value from 1 and up or -1 and down. Okay? And because it never reaches 0, it cannot cross the x-axis. All right, so let's see if we can use some of that information and make a sketch for secant. Okay, I've already put the asymptotes in. Okay, I just drew a bunch of them at pi over 2, 3 pi over 2, -pi over 2. Okay, does it cross the x-axis?
No.
Nope. So what I'm going to do is I'm going to sketch in these 2 sections here. Okay, these 3 dotted lines really give me 2 sections. All right, let's type that in and let's test a point just to the right of -pi over 2. All right, so let's type 1 over cosine. All right, so this is -pi over 2. A point just to the right of that would be negative 1.56. Okay, so I'm up very high. Okay. Let's check a point just before pi over 2. What's a value that's just before 1.57? 1.56. We're up very high again. Okay, let's check a value just after pi over 2. What would be a good number there? 1.58. This time we're down very low. Let's check a value just before 3 pi over 2. 3 pi over 2 is 4.71. I'm going to check 4.7. And we're down very low again. Okay. Somebody give me a value that I can take the cosine of, and it'll come out to 1. Cosine of
0.
Yeah, cosine of 0. Okay, cosine of 0, think about your graph of cosine. Starts up here, comes down, goes back up. So cosine of 0 is up at 1. And we said if the cosine is equal to 1, then the secant is also equal to 1. So at 0, secant is equal to 1. Okay? And what's a value I could take the cosine of and get negative 1? Pi. To take the cosine of pi, the answer comes out to negative 1. And 1 divided by negative 1 is negative 1. All right, so we get almost this symmetry. And everything here is connected with a smooth curve. So we get kind of a U shape and an N shape. And the way that I sketched it so I didn't break anything off. Okay? That's a full picture of one period of secant. Okay. What's the distance from negative pi over 2 to 3 pi over 2?
2 pi.
2 pi. It's from here to here. That's a distance of 2 pi. Okay. And let me show you how it looks on the calculator. Okay, if you do zoom 7, it breaks off part of a section. I showed you guys. Let's see, I can put it right here. Okay, I showed you guys this part right there. Okay, and if you just copy and paste that, that's what the graph of secant looks like.
So that's 1 period.
That's 1 period, yep. To get a full period of secant, you've got to have the U shape and the N shape. Okay, I'd rather you not cut it off into like a half. Technically, this is a full period too. If I drew this, this, and that, because I'm ending right where I would start again, okay, on the y-axis. But that's a half, and a whole. Okay, so together, well, actually, I said that wrong. A half, a quarter, and a quarter. So together, that does make one whole period. Okay? But I'd rather you sketch it like that if you can. Right. And because the period here is 2 pi, we're going back to our other formula. Right. So to find the period of secant or cosecant, it's 2 pi over b. Okay. So this is the one you use most of the time. Only time you don't use that is for tangent and cotangent. Right. And notice, again, secant is undefined at pi over 2. You get a vertical asymptote. So we're going to use the same reasoning we did with tangent. Set your argument equal to pi over 2. Solve it. And that'll give you one vertical asymptote. And then using the period, add or subtract the period as many times as you need to find more asymptotes. Generally, you need 3. If you want to sketch one section, you need the left, the middle, and the right asymptote. Okay, but any three asymptotes are enough to sketch one period. If you showed me a period, let's say you did it like this, that's fine. Right? If you start with the N shape and then the U shape, then show me another N shape and another U shape. Okay, if they want two periods, okay, that'd be perfect. So let's try looking at that and just figure out domain, range, period, and the asymptotes. All right, period, you guys already figured that one out. What's the period of secant? 2 pi. Okay, where's my first asymptote? We could pick anyone, but I like to pick the first one that's positive. Pi over 2. So you get an asymptote at pi over 2. And the next asymptote is at 3 pi over 2, which is how far away? Pi. The next asymptote would be how far away? From that one. Pi. And then the next one after that would be another pi units away. So we get an asymptote from pi over 2 every pi radians. Okay? So I could put, you could put plus or minus n pi. Or you really could just say plus, and n could be a negative number. And that would make it minus. Yep. So you get a vertical asymptote at pi over 2 plus or minus any integer multiple of pi. So n is an integer. Okay, what's my range?
Your range is anything from 1 and up to anything from below that.
Yep, anything from -1 all the way down to -infinity. And then anything,
Infinity have a
yeah, parenthesis, thank you. Yeah, that's important. And then anything from 1 up to infinity. Okay, so there's my range.
And it can equal 1.
It can equal 1. It does equal it, yep. And my domain, well, my domain is every real number
except for the asymptote.
except for the asymptotes. That's why I did the asymptotes before the domain. So I would write domain is all, let's write it like this. All x's except when x is of the form, and then write my asymptotes. X equals pi over 2 plus or minus n pi. Okay, so it's basically just saying it's all real numbers except when x is an asymptote. Okay. Any question on basic properties for secant? All right, let's graph cosecant. We're not going to go through as much detail. Let's just use the calculator. But since sine and cosine are very similar, secant and cosecant are going to be very similar. So if we look at it, notice in this one the y-axis is a vertical asymptote. For this one, where did I put it? The y-axis cut right through one of the shapes. So it's basically the same graph, just translated 90 degrees. Okay? That's how I would think of it. It's basically just a translation 90 degrees, or pi over 2 radians. All right, so let's, oops. What I'm going to do is I'm going to copy and paste all this because a lot of it's the same. And we'll just adjust what we need to. All right, what's going to stay the same here?
The range.
The range,
Range is going to stay the same, yep.
period.
Period's going to stay the same, and that's it. All right, so asymptotes I need to fix, and domain I need to fix. Okay, where's my first vertical asymptote here?
0.
Yeah, 0. And how often do they reoccur? Yeah, they reoccur every pi units. You could check that if you wanted. Type in 0 in your table, then type in pi, and it'll say error. So plus or minus multiples of pi. And the domain is every x value except the asymptotes. Now, technically, because the first asymptote is at 0, I could just say the asymptote is any number of the form n pi. 2 pi, 3 pi, 4 pi, negative 6 pi. I don't really need the 0, but it's okay if you put it. All right. Any question on cosecant? And again, all the transformations apply. Okay. We're not going to be doing as much sketching by hand, but I could give you a problem and say, what would that do to the original cosecant function? Okay, what would it do? Stretch it which way? Vertical. It's a vertical stretch by a factor of 3. Yep. So all that stuff still applies. All right, let's see. Find the period, and then we're just going to write down a window that shows 2 complete periods. Do I use 2 pi over b or pi over b?
2 pi.
2 pi over b. Okay, well, that's half the question. Find the period. And now cosecant. All right. Let's find our first asymptote. Actually, it's going to be pretty easy. If you don't transform cosecant, where's your first asymptote?
0.
It's at 0.
Whatever translated is
All right. So take your argument, set it equal to where the first asymptote would be, at 0, and now solve. So where's my asymptote going to be now? It stays at 0. If it was at 0, it's like if you multiply 0 by a number, it stays 0. All right. So that's probably a good x min. Right, so 1 over, let's adjust this. Okay, so x min, we could do 0. What about my x max? I want to show 2 periods. Donna? 4 pi over 3. Okay, if you went to 2 pi over 3, you'd show 1 period. Let's go to 4 pi over 3. So how many U-shapes should we see?
4.
Well, you table.
U-shapes.
Oh, 2.
2, and how many N-shapes? 2. So we should see 4 distinct shapes on the square. X min, Y min, and Y max, that's fine. It's perfect. That's what they wanted. 2 complete graphs, nothing's broken off. Okay, again, not the only way to do it, but probably the easiest. All right, so window. X max was it 4 pi over 3? You could just leave that as your window. And you don't have to write the scale or the resolution. I would just ask for this one, this one, this one, and that one. Okay. Okay, any questions on that? All right, so summary, again, if you already took the notes, you have this. For sine, cosine, secant, and cosecant, it's 2 pi over b. If b ever happened to be a negative, it's always absolute value. Okay. But when we studied b, it never was negative, so we didn't need absolute value. But if it ever is, you always just take the absolute value of it. Okay, a period is a measurement of a length. So you'd never have a negative period. For tangent and cotangent, use pi over b. Okay, t equals pi over b. All right, so last thing we're going to do, easiest part for today is just solving things on the calculator. And we just have to make sure you understand the idea that if you have one solution to a trig function, because a trig function repeats, you have infinite solutions. Okay, so if you can find one, you can find infinitely many. Okay, the goal is basically going to be find all the solutions in one period and then put plus a multiple of the period, okay, adding or subtracting. Kind of like we did the asymptotes, right? Same idea. Okay, so suppose that you graph it. You find a solution in a period, we'll call it x. All the solutions would be of the form that solution, x, plus your period times n. Okay? Your solution plus any integer multiple of the period. Okay, and again, you don't have to worry about doing plus or minus, right? Because if n is a negative, that would take care of the minus. Right, so let's find all solutions to where cosecant equals negative 1.6. All right, James, since I don't have a button for cosecant, how do I type that in? Yep, but there's no button for CSC on the calculator.
Oh, it's
So, yeah, it's 1 over sine. So that's important. Make sure we remember how to type that. Okay, I'm going to put that in y1. What would I put in y2? Negative 1.6. And now, they're not telling me a window because they want all solutions. So you need to find your own window that's 1 period long. Okay? Find all the solutions in 1 period. And then we can go from there. So what would, what's the period of cosecant? 2 pi. All right. So if you forget, wait, is this where the vertical asymptote is the y-axis, or is this the one where it's 90 degrees off? Just try 0 to 2 pi. Okay. Try it. See if you get a nice looking window. If not, then it's the one where it started at pi over 2 as your first asymptote. Okay? But this time, 0 to 2 pi worked perfect. Okay, let's find the two solutions by doing what? Intersect. Right, so we get about 3.82. And the second one, we get about 5.61. Now, what am I going to put after the 3.82 and the 5.61 to show all solutions?
Add 2 pi n.
Perfect. Add, and n could be negative, so that takes care of the subtracting. That answer is going to repeat itself every 2 pi, okay, every period. And how about this answer? Same thing. That answer will repeat itself every 2 pi. Okay, any questions on that one? All right, so let's finish up with tangent x equals 2.5. All right, Derek, what do I want to put in y1?
In y1, you're going to want to put tangent of x.
Tangent of x. All right. David, what about in y2? 2.5. What would be a good window that just shows me 1 period of tangent?
0 to pi.
All right. So 0 to pi. So technically, is that one period?
Yeah.
Yeah, it is one period and it's okay. But if this was a problem where I was asking you for a nice window that shows one period, this wouldn't be it. So I like the difference between the x min and the x max.
I don't care if we
Okay, we could shift it that way, or what else could we do? We could shift it back. So if you did negative pi over 2, positive pi over 2, that's fine as well. Either way, it's going to give you one period nicely now. Okay, and it doesn't matter which period you find an answer to. Okay, whether you find this one, or you find the one before it, or the one after it, as long as you put plus whatever you should on the end, that's going to cover all the solutions. All right, so let's see what we got. Second calc, intersect, get about 1.19. And what would we put on the end of that? Pi n. Okay, why not 2 pi? Right. Period here is just pi. Okay. So be careful on the test. If they ask you to find all solutions, I want something like this. If I want you to find solutions between 0 and 2 pi, that means I want you to list every single answer out between that window. Okay, any questions on that? All right. So homework, again, tonight will be in the book. Okay, it's 352. Okay, 236, 7 to 10, 13, 15. 20, 28, 29 through 31, 34, and 45 through 48. All right, so we'll take a look at that first thing tomorrow. We have our test tomorrow is just on what we did this week, 6-3, 6-4, and I will be here after school for extra help today.